Barcelona. Dr. Busquets is a biochemist, molecular biologist by training, and he will tell us about the Toy Kit Against Malaria.
Okay, thank you, Reto, for the introduction. And our Nanomalaria unit is a small group which actually belongs to two institutes, a nanotechnology center and also a center which is devoted to the clinical aspects of neglected diseases. And this is why the driving force of our group is the application of nanomedicine to a disease like malaria. But actually, if you introduce into a server like Web of Knowledge the words nanomedicine and malaria, you only get a handful of papers, maybe not even 20 when I looked last week. And probably this is because there is still the idea that nanomedicine is too expensive to be applied to diseases of the developing world, as Reto has advanced before. Probably also there is the misconception that nanomedicine is always something which goes towards the design of kind of nanomachines that are more or less complicated, and this obviously it's very costly. But as I will try to show you, this is the evolution of our group in the last 6 or 7 years, which has gone from an original idea that actually started very close to this, to a more practical design, which is bringing us closer to something that can be applied in the clinics for malaria. Here I have to say that, as Reto also mentioned, there must be implication from politics, also from pharma industries, obviously, and from funding agencies, but also the researchers, we can do something there, and is maybe using a bit of ingenuity to design, in our case, nanovectors that are as efficient as a very expensive machine, but with a much smaller cost. In the case of malaria, I will not go into the details, but one of the problems with the disease is that the life cycle of the causing agent, which is a protist of the genus Plasmodium, is very complex, and it happens in two hosts, the human and in a mosquito. And although this is indeed a complication, as I will show in the last part of my talk, this might give us the opportunity to treat the disease in a more successful way. The obvious advantages of using a targeted delivery of antimalarial drugs is what everybody knows in this audience, which is if you can give lower overall amounts, you might not have side effects on the organism. But if you can give highly concentrated amounts where the parasite is, then you can eliminate or you can limit greatly the evolution of resistance, which is actually, I think, the main objective of any targeted drug delivery strategy. Not to mention that if you have such a tool in your hands, maybe you could use orphan drugs that maybe they are highly toxic and that they cannot be used, that they might be actually very good antimalarials, if you are able to deliver them just to those cells that you want. This is, as I mentioned before, when we started 6 years ago, we thought very naively that we could design a type of nanovector that could take an antimalarial that must act on the malaria parasite by designing a nanovector that can help the antimalarial drug to cross all the different barriers that the parasite builds between itself and the extracellular milieu. Like, first you have the infected red blood cell membrane, then you have a parasitophorous back wall where the parasite lives, you have also, obviously, the cell membrane of the parasite, and so on. So we thought, okay, no problem. We can build a nanovector, maybe a liposome, where we will add targeting molecules, and then we can introduce a second nanovector that has another targeting molecule against the Parasitophorus vacuole. But when we showed this idea to the pharma companies, they said, okay, forget about this. This is too complicated for malaria. You have to come up with something much simpler. Then we reduced our original idea to just 2 steps that are essential for any targeted drug delivery strategy. One is that you can target your cell. Obviously, your nanovector has to somehow bind to your cell, and if possible with a good specificity. And secondly, you must be able to inject into the cell this, the drug that you are using. This is what we call our Russian doll strategy, in case we really needed to have several nanovectors, one inside in another, like in a Russian doll. But as you will see later, this, we didn't have to reach such a complication. Actually, our first trial was relatively successful. This is the idea of the magic bullet, which was actually introduced for the first time by Paul Ehrlich more than a century ago, which was the concept that you could target your diseased cell with complete specificity without harming the cell next to it. And to illustrate our success in this in vitro assay, here I show you the result of our immunoliposomal prototype, sorry about that, where we had a liposome with targeting antibodies. And to show that we could be 100% specific, that we had a magic bullet, we loaded the liposome with a fluorescent marker. And as you can see here, when we add this to a culture of living cells, we have most of the cells as a non-infected red blood cell. And we selected this field because we had a single Plasmodium infected red blood cell. And as you can see by the label of the targeting antibody, which is specific for this cell type, and the nuclei label, which tells us where is the infected cell, and the quantum dots, which is the fluorescent content of our immunoliposome, we had a complete specificity regarding targeting. The problem was that when we substitute an antimalarial drug for the fluorescent compound, that was not so successful. We had to add a lot of antibody to our immunoliposome, and not even with the highest targeting antibody, we could reach a complete elimination of the parasitemia. And this was even worse when we tried in vitro assays. We were never able to clear the parasitemia from a mouse which had been infected by malaria. And in addition, when we made our calculations, this was very expensive. What we used as a measure is how would it cost to eliminate 50% of the parasitemia from 1 liter of infected blood, and the increase in cost for a good antimalarial like chloroquine was 51 euros. That was completely unusable in a malaria setting. So we didn't have actually a magic bullet. At most, what we had was a magic tickle to the cell, because with what we could do, we could not actually impact on the parasitemia of a mouse, for instance. Then we are still very far from a magic bullet, but essentially we think that what we have to do is to take our original immunoliposomal prototype, and as in a Lego game, you just have to exchange your 3 main parts, namely your nanocapsule, your antimalarial drug, and your targeting element, and try to advance towards a working prototype, that it's cheaper, but that it works as efficiently as the most expensive nanomachine that we saw in the beginning. Our first idea, because the antibody was what clearly increased the cost of our immunoliposome, was to change the targeting molecule, and then we were looking for cheaper alternatives. And one of them we tried was heparin. Heparin is very abundant, it's very easy to obtain. And some years ago, it was described that heparin was actually a relatively good antimalarial. And then we said, okay, if something is antimalarial, it must have some type of targeting towards our desired cells. And we did some force spectroscopy experiments where we actually could show that indeed heparin was very, very specific for erythrocytes infected by Plasmodium, but not at all for healthy erythrocytes, as we could also see by fluorescence microscopy. So what we did, obviously, was to simply exchange our antibody by heparin, just by making liposomes with positively charged lipids, because heparin is the most negatively charged natural molecule. We had this type of liposomes, which actually were very good in having a dual activity, because we could see that we had in these liposomes that had heparin as targeting molecule and that contained an antimalarial drug, we had the addition of both activities, that of heparin being an antimalarial in itself, and that of heparin being a targeting molecule, which increased significantly the activity of in this case, primaquine. The result was that we could reduce significantly the cost, and now we went down to €1. And in the future, we are planning to use molecules similar to heparin, but derived from marine organisms that might even make the model even better. The big problem of liposomes, however, and that's why probably our mice assays didn't work, is that we had, it was an intravenous administration, what we had to do, and that's not so good for malaria nowadays, where you would need, if possible, oral administration. And for that, liposomes are very bad. Then we started to try other types of encapsulating elements, like polymers, in particular different types of polymers, and I show you here briefly our results with polyamidamines, which are a type of polymers that they gave us relatively small nanoparticles, but which in some cases they had a specific targeting as if they contain an antibody or heparin, but they didn't. The surprise was that some of these polymeric structures, they have also specific targeting towards Plasmodium-infected red blood cells versus non-infected erythrocytes. And here the results in vivo were really good, because in this case, because this was still, this was intraperitoneal administration, so we are not yet in the oral administration, but where chloroquine alone didn't have any effect on mice, this is here, the same amount of this antimalarial drug encapsulated in polyamidamines was able to completely cure the animals. So I think we are getting closer to something that might work. This is more close to the concept of Trojan horse, because these polymers, they did really enter the cell, and once inside the cell, they started releasing the drug, which was what killed Plasmodium. And still better, here we could go down already to 40 cents of euro, which allowed us to increase the efficacy of chloroquine, where with the immunoliposome, if you remember, that was much more expensive. And finally, we are now trying with another type of polymers, which are dendrimers, that are polymers that grow in a more controlled way. And in this particular example, I show you here that with some of these dendrimeric structures, we were able to lower in vitro considerably the IC50 of chloroquine and also of primaquine. We are not yet in vivo results here, but when we make our calculations for the dendrimeric efficacy, we are down to half a cent of euro. So as you can see, from our humble research activity, we are getting closer to something that can be used in a clinical setting. We think now we are waiting for the politicians, pharma companies, and funding agencies that can make this possible. And finally, our next step would be to move away from the red blood cell Actually, the number of red blood cells in a human infected with malaria is so huge, is several trillion, that it will be very difficult, probably, to clear with this type of strategies the malaria infection from a human. But the great opportunity that the cycle of Plasmodium gives us is that the life cycle of the parasite is shared with the mosquito. And you will tell me, okay, the mosquito is where the parasite is at its weakest by the number of cells. In an infected mosquito, you might have, for some of the stages, just 2 to 5 cells. And you will tell me, okay, but then you have trillions of mosquitoes to reach, which is true. But I think the great advantage here is that if we can design a medicine that has to be delivered to the mosquito, that doesn't have to go through the human, we can skip all the clinical assays, and we might have something that can work in the field in just a couple of years and not in a couple of decades. And this is where we tried a very simple experiment. We gave to mosquitoes one of our polymeric nanovectors in the sugar mill, and the idea was simply to see if we could see those nanovectors exiting the stomach of the mosquito and distributing through the body of the insect, and if possible, going to the salivary glands, which is where the sporozoites are waiting for the infection to the next human. This is actually what happened. We gave this nanovector to the mosquito, waited for a couple of days, and then by fluorescence microscopy checked where the nanovectors were. And this is our most successful attempt. This is the mosquito, this is the thorax, and this is where the salivary glands should be. And as you can see, the green label of the nanovectors is actually in what we think are salivary glands. So we think we are in the right track to target mosquito stages. The final message is that no matter if we talk about magic bullets, Russian dolls, Lego, or Trojan horses, we think that nanomedicine can be really an option for diseases of poverty. And this is simply to acknowledge people who made possible this work and our funding agencies, and thank you very much for your attention.
Thank you very much for this really promising talk. Exactly what we need. A question over there.
Thank you so much for that interesting presentation. Your nanovector, the very last slide before this, are you looking at just the adult phase of the mosquito, or do you have a target to the larval stages, like when they're yet in the water?
We are looking at the adult. We didn't do anything yet with the larval stages because actually we didn't think yet about that, but our idea for as the strategy for the delivery of those nanovectors would be to have some type of container that we could hang on the walls of malaria endemic areas, and then this is designed for the adult mosquitoes to go there after a blood meal and maybe bring something from there where our nanovectors would be waiting. Because the idea of targeting larvae, I think then we should think about wet areas where those larvae grow, and we might have to consider them spraying those areas with the nanovectors, and that might again increase very much the cost. And I don't know if we could then wait to reach as many mosquitoes as if we are thinking about adults. But we didn't think too much about it, so it might be also a good idea to target larvae.
Yeah, that's good. Interestingly, in my unit, we have a platform. We're also looking into, the entomological aspect of this. And if I may ask, do you know the mechanism of action? Is it affecting the fecundity of the mosquitoes or longevity? The mode of action of your target, of your drug, of your nanovectors?
No, we didn't load any drug here. This was just a container which was devoid of any drug. We just wanted to see if we could have a container reaching those parts of the mosquito where the parasite is, but we didn't do yet the experiment of loading this container with any drug.
Thank you.
So one final question.
Sorry. Hello. Don't you see specific uptake of small molecules to infected red blood cells and not normal red cells?
Yes, that is something that we have been realizing lately.
Okay.
And actually, we have applied for projects where we say we want to look for a very specific targeting molecule to infected red blood cells. But actually, we see that many different types of molecules, large polymers and small molecules, they do seem to enter very easily into the infected red blood cells. So what we came to realize now, and we make it explicit in our next project, is that we start caring too much about finding a good targeting, because actually many different things will enter that type of cell. And we start caring more about what type of anti-malarial drug we are going to work. There you are absolutely right.
Thank you very much, Xavier, again.